Welcome to the deep dive. Today, we're setting out on a pretty unique kind of theoretical scavenger hunt. We're looking for a particle. Well, not exactly looking for it in the wild.
Right, more like trying to build it.
Exactly. Physicists are trying to construct this thing, the Majorana fermion, because it might just be the key to, well, revolutionizing computing.
It's a huge deal.
So our mission today is to explore this elusive entity and why everyone's so keen on making it exist in the lab. We're using C.W.J. Benneker's 2011, well, updated in 2012, review as our main guide. It's sort of the foundational text, isn't it?
Oh, absolutely. It really laid out the landscape. And the reason for all this effort, this obsession almost, it boils down to one word: stability.
Stability for quantum computers.
Precisely. These Majorana fermions, if we can make them and control them, they promise a way to build topological qubits. And those could solve the massive coherence problem. The way quantum states just fall apart so quickly in current systems.
Okay, so let's unpack that. Starting with the particle itself. Majorana fermion sounds exotic. Where does the idea even come from?
It comes from fundamental particle physics way back. Ettore Majorana proposed it nearly a century ago. The core idea is, well, it sounds impossible at first. It's a particle that is its own antiparticle.
Its own antiparticle. Usually matter and antimatter annihilate, right? Electron meets positron, poof.
Exactly. But for a Majorana, there's no distinction. It is its own opposite. Now, whether such a fundamental particle actually exists out there in the universe, that's still an open question for high-energy physics.
But condensed matter physicists aren't waiting around for that discovery.
No, they got clever. They realized maybe we don't need the fundamental particle. Maybe we can create something that acts like one.
An imposter particle.
Sort of. More accurately, an emergent excitation. It's not a basic building block of matter itself, but a collective behavior of electrons and holes. The absence of an electron inside a specially engineered material.
So like a wave on water isn't the water molecule, it's a behavior of the water.
That's a great analogy. We're coaxing the electrons and holes in a solid to behave in this very specific collective way that produces an excitation. And this excitation, mathematically, physically, it behaves just like a Majorana fermion.
Okay, constructing a wave. How do you do that for a Majorana? Benneker's paper lays out the recipe, you said. What are the key ingredients?
You need two crucial things to make this happen, to blur that particle antiparticle line. First, you absolutely need a superconductor.
Why a superconductor?
Because superconductors fundamentally mess with the concept of charge. Inside a standard superconductor, electrons pair up, and charge isn't conserved locally in the same way. It basically hides the main difference between electron negative charge and a hole effectively positive charge.
Okay, so the superconductor hides the charge difference, but that's not enough on its own.
Nope. You need a second, more subtle ingredient: topology. Think of it as a kind of geometric property of the quantum state of the electrons.
Topology, like Mobius strips and donuts. How does that apply here?
Yeah, same mathematical field. Here it relates to the energy levels. You need this specific topological property, often related to something called a Berry phase, to eliminate any leftover energy, even from quantum fluctuations, the zero-point motion. You need to force the state to exist precisely at zero energy.
Zero energy.
Exactly zero energy, right in the middle of the energy gap that the superconductor creates. When you combine the superconductivity and the right topology, these special zero energy states can pop up. And those states are our Majorana excitations. They're often called mid-gap states.
Wow. Okay, that's some serious theoretical footwork. But, like you said, there's a huge motivation. Let's get back to the quantum computing angle. Why is this zero-energy, charge-neutral excitation such a big prize?
It's all about what happens when you have a pair of them and you keep them separated, say bound to opposite ends of a special nanowire or attached to specific defects in the material.
Separated Majoranas. What's special about the pair?
The quantum information isn't stored in one Majorana or the other. It's stored non-locally, across the pair. And the way this information behaves is governed by something truly weird and wonderful: non-abelian exchange statistics.
Non-abelian. Okay, that sounds complicated. Break that down for us. What does it mean for computation?
Right, it's not the most intuitive name. Abelian basically means order doesn't matter, like 2 plus 3 is the same as 3 plus 2.
Right.
Non-abelian means the order does matter. Think about braiding ropes.
Braiding.
Yeah. If you have, say, 3 ropes and you swap the first and second, then the second and third, the final pattern is different if you swap second and third than first and second. The final state depends on the sequence of swaps, the history.
So swapping these separated Majoranas around each other, the path they take matters.
Exactly. That's the core idea. The quantum state, the information in your qubit, is encoded in the topology of the braid, the history of how these Majораnas were moved around each other.
Mm.
It's not stored in a local property like the spin of an electron, which is easily disturbed.
So the information is stored in the process, in the geometry. How does that protect it from noise? That's the key, right?
That is the absolute key. Imagine some local noise source, a stray bit of heat, an electric field fluctuation hits one of the Majoranas. Since the information isn't stored there locally but is spread out across the entire braid history of the pair, that local nudge can't easily corrupt the encoded qubit.
It can't see the whole picture.
Pretty much. To corrupt the information, you need noise that acts globally and in a very specific correlated way across both separated Majoranas simultaneously. That's much, much less likely than random local noise.
So the information is inherently protected by its non-local topological nature.
That's the promise of topological quantum computing. You get qubits with potentially massively longer coherence times. They're naturally robust against local errors. It's fault tolerance built right into the hardware.
Okay, I'm sold on the why. Now the how. If these things need to be constructed, engineered, what are the blueprints? How do you actually make these topological superconducting systems Banachir describes?
Well, there isn't just one way. The field has explored several routes. Initially, people looked for naturally occurring materials that might just have the right properties, things like chiral P-wave superconductors.
P-wave. That sounds like an unconventional type of superconductor.
It is very exotic,
Mm-hmm.
very hard to find and confirm, let alone work with. They have a specific kind of electron pairing that theoretically should have the right topology built in. But yeah, experimentally, very challenging.
So people looked for other ways, workarounds.
Exactly. The focus shifted towards engineering the properties by combining known materials, stacking things together in clever ways. For example, using the Shockley mechanism. That's about creating special electronic states on the surfaces or edges of materials that have topological protection.
And layering different materials. That seems common in advanced electronics.
Yes, that's become arguably the most promising direction. Building semiconductor heterostructures. You take a semiconductor nanowire, one with strong spin-orbit interaction that's important, but put it very close to a standard, simple swave superconductor.
Like aluminum, something common.
Yeah, exactly. Then you apply a strong magnetic field. The combination of the semiconductor's properties, the superconductivity leaking in, and magnetic field can conspire to force the electrons at the interface into a state that mimics that P-wave superconductor. It creates a topological superconducting state artificially.
Wow. So you're building the exotic physics from simpler parts.
That's the idea.
Yeah.
Another approach uses topological insulators. These are materials that are insulating inside, but have conducting surfaces with topologically protected states already. You combine those with superconductors too, trying to leverage their natural surface states.
It sounds incredibly complex, getting all these ingredients, materials, fields, low temperatures just right. You mentioned the paper has like 13 figures just on the how-to.
It really highlights the difficulty, yeah.
Yeah.
This isn't just sketching on a blackboard. It's intense materials science, nanoscale fabrication, ultra-low temperature physics, controlling interfaces at the atomic level. Each figure represents years of theoretical modeling and experimental effort trying to optimize these delicate structures.
Okay, let's say the engineers succeed. They build the perfect structure, cool it down, apply the fields. How do they know if they've actually created Majorana fermions? If they're charge neutral and zero energy, they seem kind of invisible.
Right, they don't exactly wave a flag. You need specific, telltale experimental signatures. Things that only a Majorana fermion, particularly one sitting at the end of a wire, a zero-dimensional Majorana Zero Mode, could produce.
The smoking gun evidence.
The most famous proposed smoking gun is half-integer conductance quantization.
Half-integer. Conductance usually comes in whole steps, doesn't it? Based on fundamental constants E2 out.
Exactly. Normally, conductance through a quantum channel is quantized in integer multiples of 2 ert. The 2 is for spin. But theory predicts that a single, isolated Majorana mode at the end of a wire provides a unique resonant channel for electrons tunneling through it. And this channel contributes precisely half of the fundamental unit, 1/8 or 0.5 times 2ah8.
So if you measure the conductance as you change, say, a voltage, and see a stable plateau exactly at half the normal first step.
That's considered very strong evidence for a Majorana Zero Mode. It's been a huge focus of experiments for the last decade or so.
Are there other fingerprints? What about proving that non-local property?
Good point. The half-quantized conductance is a local probe. To test the non-locality, you look for things like non-local tunneling conductance. If you inject electrons at one end of the wire where a Majorana is supposed to be, you should see measurable effects, correlations, in the current measured at the other end, where the partner Majorana should be. It shows they're linked, even though separated.
Okay, that makes sense. Any others?
Yeah, a couple more key ones mentioned in the review. One involves the Josephson effect. That's the flow of supercurrent between two superconductors separated by a weak link. Normally, this current depends sinusoidally on the phase difference across the junction with a period of 2.
Right.
But if Majoranas are involved in carrying that current across the junction, the periodicity is predicted to change to 4. A 4-periodic Josephson effect. That's another unique signature tied to their nature.
Double the period.
Yeah.
Interesting.
And finally, there's a thermal signature. These zero-energy Majorana modes should affect how heat is conducted at very low temperatures. Their presence could lead to a specific kind of thermal metal insulator transition, giving a thermodynamic way to detect them.
So multiple lines of evidence are needed, really.
Ideally, yes. You want to see several of these predicted signatures in the same device to be truly confident.
Okay. Create them, detect them, then you have to use them. This involves that braiding idea. How on earth do you physically braid quasi-particles inside a solid? You can't just pick them up and move them.
No, you can't. The braiding happens by manipulating the environment that creates and binds the Majoranas. Remember, they're often bound to the ends of wires or specific locations defined by electrostatic gates, tiny electrodes placed near the material.
Like switches?
Kind of. By carefully turning these gate voltages on and off in sequence, you can effectively move the potential well where the Majorana is trapped. You can nudge it along the wire, make it swap places with another one by guiding them around each other through junctions, like trains in a rail yard.
So the braiding is done electrically by controlling the gates.
That's the plan. A sequence of gate voltage changes corresponds to a specific braid, which performs a specific quantum computation, a quantum gate. It's all controlled electronically, manipulating the paths of these emergent particles.
And after the braiding, you need to read out the result.
Right, the readout phase.
Yeah.
That typically involves bringing the Majoranas back together or coupling the topological quivet state to a more conventional measurement circuit, maybe another superconducting quivet or a quantum dot, to determine the final state, the outcome of the computation.
It's just incredible, the whole concept. Building a potentially revolutionary computer based on essentially carefully controlled waves in a solid that mimic a particle that might not even exist fundamentally.
It really is a testament to the power of condensed matter physics and materials engineering. And, the pace Ben Anker's paper helped set was intense. That V2 revision just a year later, adding experimental updates, that showed how fast things were moving even then.
A race to build a stable quantum future on a foundation of constructed reality.
You could put it that way. And it really makes you think, doesn't it? This whole search for Majoranas and materials forces us to reconsider what we mean by a particle or a fundamental building block.
How so?
Well, it raises this a fascinating question, something for you to ponder as the experiments continue. Could it be that an engineered quasi-particle, something like a Majorana fermion that we literally force into existence in a lab, could actually be more technologically useful, more stable, more controllable for building things like quantum computers than any truly fundamental particle that nature just gives us? It's a provocative thought that maybe the best building blocks aren't found, but made.